this better? Oh. I don't know. Should it? Hey?
Yeah, try to put it on like maybe your t-shirt or like outside.
Like this?
I think that should be better.
Oh, okay. Sorry. Do you hear me? Okay, great. Okay. So, hi everyone, thanks for attending this talk, and I would like to tell you about our work on understanding the benefits which sandboxing provides to the developers of low-level applications. So let me start by introducing what do I mean with sandboxing. So in practice, it's often the case that an application is split into different parts. So you have some parts which are trusted, maybe you wrote them yourself, and there are some other parts which you don't trust, maybe some libraries which you downloaded from the internet. But these two parts need to interact with each other. But if you do this naively, this can be very dangerous, especially in a low-level setting. So for example, in a low-level setting, this untrusted code could try to attack the private memory of the trusted code and override it with bad values. Or it could try to issue malicious system calls and take over your system. So what's often done in practice is to use sandboxing. And what sandboxing does is it isolates these untrusted parts inside an application. And more concretely, sandboxing usually consists out of memory isolation, which prevents these attacks against the memory of the trusted code, and system call isolation, which prevents the untrusted code from directly issuing malicious system calls. And there are many different techniques for sandboxing which are used in practice. So what you usually do when you have such a technique for sandboxing is you convince yourself, either formally or informally, that this technique actually gives you system call and memory isolation. And there's actually quite a bit of prior work which even formally shows that certain specific sandboxing techniques give you system call and memory isolation. However, this is not the end of the story, right? At the end of the day, you don't care about whether your program uses system call or memory isolation. You care about safety guarantees for your program. And now the question is, when you have system call and memory isolation, how do you get to safety guarantees of a program? And this is unexplored territory so far. So this is where we come in. We try to answer the question, which benefits does sandboxing provide for proving safety guarantees for a program? And we especially focus on making this independent of the concrete sandboxing technique used. And this is non-trivial, as we see in a moment, as there exists attacks which are not prevented by sandboxing directly in this setting. We will see later how we can prevent them. But first, we want to prove safety guarantees for programs. So first we need to define what do we mean with safety. And it's usual to define safety as crash freedom, maybe in some small step operational semantics, but we cannot really do this here because the untrusted code, it can try to do bad things, like it can try to access unallocated memory and crash the program. And we cannot really do anything against this, so we cannot really define safety as crash freedom. So what do we do instead? So what we care about for a program is how the program interacts with its environment. And in this low-level setting, the interaction with the environment is the system calls. So we define in this work, we define safety via the traces of system calls produced by a program. So let's say you have for example, you have open, read, and close system calls for interacting with a file system. You might care about the safety property that you only call read and close on open files, and you can formalize such safety properties as automata, as for example, this automaton formalizes the safety property. In our work, we are generic over safety properties formalized as such automata. So now that we've seen what we mean with safety, let us see possible attacks against this safety. So the first two attacks of the untrusted code, pretty obvious. So the trusted code can try to directly issue a bad system call, like read with a bad file handle, or it could try to guess some location, like we're low-level setting. Untrusted code can guess location of the trusted code, write a bad value to it, and use this to violate safety. But these direct attacks we've already seen, they are directly prevented by the sandbox. So the first attack is prevented by system call isolation, and the second one by memory isolation. However, there's also another class of attacks, so-called confused deputy attacks, which are a bit more subtle. And these are attacks via the functions which are exposed by the trusted code to the untrusted code. So let me show you an example. Let's say the trusted code wants the untrusted code to be able to close file, so it might have a function to close and expose it to the untrusted code, which allows the untrusted code to close a file. However, if it's done naively, like here, this opens the trusted code to attacks, where the untrusted code can call this doClose function with a bad file handler and use this to violate safety. Also, the trusted code might have a function to initialize the struct somewhere memory, which is a very commonly found pattern in low-level languages. And if the trusted code exposes such a function to the untrusted code again can attack the trusted memory by passing a bad location. So what's common about these attacks is these are kind of indirect attacks, where the untrusted code, it's not directly the untrusted code which is doing the attack, but the untrusted code confuses the trusted code to do the attack itself. And because the trusted code is not restricted by the sandbox, these kinds of attacks are not prevented by the sandbox. So we will actually see later how we can actually prevent these kinds of attacks in our setting as well. But let's look at our contribution of what we did in our work. So first we want to reason about sandboxing independently of the technique. So we actually provide a formal semantics of sandboxing, which is independent of the concrete technique used. And then we use these semantics to show how you can prove safety of programs which use sandboxing and under which conditions you can achieve safety. As a third point, we show how we can prevent these indirect attacks which the untrusted code can still mount in this setting. So let's start with this formal semantics of sandboxing. We give this via small step operational semantics of a language lambda sandbox which has sandboxing built in. So let's go back to the big picture from the beginning. We had the trusted and the untrusted code, and they're both represented by some functions which they expose to each other in some interface I. And there's this gated call instruction, which we've briefly seen before, which allows the trusted code to call the untrusted code and vice versa. And such a call gate mechanism is very commonly found in sandboxing techniques used in practice, and it allows us to keep track of whether currently the trusted or the untrusted code is executing. The next thing which we need to model is the memory, and we do this by splitting the heap into two parts, one part for the trusted code and one part for the untrusted code, and we do this by extending locations with an additional bit which tells us whether this location points to the trusted or to the untrusted heap. And this models coarse-grained memory isolation, which is the most commonly used form of memory isolation found in practice. We've also seen, we also need to model this low-level setting where the untrusted code can try to attack the trusted heap by guessing a location. And we do this by adding a make location instruction to our language, which allows the untrusted code to basically cast integers to pointers and then use this to guess a trusted location and write to it. But we've also already seen that this direct attack is directly prevented by memory isolation, which we model by saying that when the untrusted code, so this add untrusted means that the untrusted code is executing this statement, when the untrusted code tries to write to the trusted heap, then this crashes the program, and so this way this attack is prevented. And remember, we are fine with crashes. We only care about these system calls. So now we've seen how we model the memory, and the last missing piece are the system calls. So we have a very straightforward model of system calls, where system calls basically are just a name and an argument, and they get recorded on a trace pi, and we will later use this trace to determine whether the execution of a program was good or bad according to the safety property which we care about. And to model system call isolation, we just say whenever the untrusted code tries to execute a system call directly, it crashes the program. So now that we have our formal semantics, we can try to prove safety of programs in these semantics. So let's think about under which conditions can we actually hope to achieve safety. So the first thing is that the trusted code is not restricted by the sandbox. So we need to verify the trusted code to maintain the safety property. Otherwise, it won't be possible for this whole program to be safe. On the other hand, we don't want to have any condition on the untrusted code, except that the untrusted code is a program of the language, which means it's restricted by sandboxing. So the untrusted code, we don't have any requirement that it is well typed or something. It can be arbitrary. Yeah, we model untrusted code as arbitrary code. But this in turn means that whenever the untrusted code passes a value to the trusted code, this value can also be arbitrary, and the trusted code must be able to handle these arbitrary values from the untrusted code. So actually, as we will see in a moment, these two conditions on the trusted code are enough to prove safety. But before we can see this, we must first see how we can actually formalize these two conditions. So our first condition is that the trusted code must be verified to maintain the safety property SP. And to do this, we use a type system which is parameterized by the safety property. And this type system enforces that during the execution of E, SP is maintained. So to be a bit more concrete, we care about safety properties which are stateful, right? So in this file example, a file can either be open or closed. So we use an affine type system to verify this stateful safety property. So if we look, for example, at this open, read, and close function in our type system, we can type them at these types where we use this abstract file type, which represents an open file handle. And the crucial part is that this file type is non-duplicable. It's an affine type, which means that whenever we pass it to close, we cannot use the file anymore, which is exactly what we need to enforce this safety property. So now that we've seen how we can verify the trusted code with our type system, let us look at the second condition, which is that the trusted code must be able to handle the arbitrary values from the untrusted code. And we formalize this using the type any, which is inhabited by arbitrary values. Every value of the language inhabits this type. So this means that whenever the trusted code receives the value from the untrusted code, it sees it at the type any, so it must be able to handle arbitrary values. And this occurs in three places. So the first is that when the trusted code has a function in the interface, the untrusted code may call this function with an arbitrary value. So the argument type of this must be any. Also, when the trusted code reads from the untrusted heap, it might read an arbitrary value. So this read is typed at type any. And the last point is that when the trusted code calls the untrusted code via gated call, the untrusted code might return an arbitrary value. So this gated call instruction is typed at type any. And I especially want to highlight this rule because this typing rule shows that we can type code which calls the untrusted code, which basically means that calling the untrusted code is safe in our type system. And proving the soundness of this rule is actually a big part of the soundness proof of our type system. So now that we have seen these two conditions, how we can formalize them, let's look at the main theorem of our work, which is actually a robust safety theorem. So robust safety is a very well-known notion in the security literature, which means safety in the presence of arbitrary untrusted code, which is exactly what we want here. So we prove a robust safety theorem. Now if we look at the theorem, we see that we have two conditions. We have the conditions on the trusted code represented by the function main and the function in the interface G. And the conditions tell us that the trusted code must be well typed, which is the condition which we've seen before. And we also see that the functions in the interface, they need to be able to handle any as the argument type. So once we fulfill these conditions, we get the payoff. And this is that if we execute the function main and it produces a trace of system called pi, then we get that pi fulfills our safety property SP, which is exactly what we want. This is our definition of safety. So with this theorem, we can show that a program is safe to execute. And I especially want to highlight not what's here in this theorem, but what's missing. And what's missing is any restriction on this untrusted code represented by the functions f. So this actually makes our safety theorem robust. So now that we've seen how we can prove safety of programs which use sandboxing, let us go back to these indirect attacks and how we can prevent them. So if we go back to our file functions, open, read, and close, we have that the trusted code might want to expose them to the untrusted code. But we see, if done naively, this is unsafe, right? Because as we've already seen before, the untrusted code could call, for example, close with a bad file handle. And formally, we see this because these functions don't have any as its argument type. So the question is, we have these functions use informative types. How can we transform them to function of type any to any such that we can safely expose them? And to do this, we use wrapping. So our goal is we want to convert functions which use informative types tau and tau prime to function of type any to any. And we do this by allowing each type to provide an import function which tells you how to convert from any to tau, and an export function which tells you to convert from tau to any. And once you have these functions, you can easily wrap a function by first calling import on its argument, then the original function, and then export on the result. And to some of you, this might seem very familiar. This might seem very similar to higher-order contracts and gradual typing. So I want to highlight some key differences. So one of the biggest differences is that we are working in a very different setting. So we are in a low-level setting with sandboxing, whereas the other work usually works a high-level language. So we, for example, have these disjoint heaps, and we need to care about copying between these disjoint heaps and checking pointers. Also, we have an extensible and affine type system, and what's important is these import and export functions, they are basically arbitrary functions. They only need to be well-typed at these types, but we don't have any additional requirement, which means they can transform the values which flow through them. And we will see in the next example how this is very useful, especially together with this affine type system. So if we come back to our file type, which, as you remember, is the type of open file handle, type of open file handles, and it's an affine type. So the question is, how can we check when the untrusted code gives us a value, whether it's a valid file? And at first it seemed very hard, because you cannot just see whether it's a valid file by looking at the value. So what do? So what we do is we use dynamic sealing and do a novel adaptation of dynamic sealing to this affine setting. And so the first observation is that the untrusted code cannot open files directly, but instead the files must have come from the trusted code. So we can do something when the trusted code exports a file to the untrusted code, we create a fresh token and then pass that token to the untrusted code. The untrusted code can then use that token to pass it back to the trusted code. And we use this association to check whether this token is valid. And we can retrieve the file from the association. But the important point is that we also removed this association. So when the untrusted code passes this token again, now this check will fail, which means that, ensures that this file type is affine. The untrusted code cannot duplicate it. And this, actually, in the paper, we also show how we can generalize this thing to arbitrary affine types. So to sum up, we've seen Lambda Sandbox, which is our formal model of low-level sandboxing, and we've seen how we can prove robust safety for well-type code, which uses the any type, and we have also seen how these wrappers can prevent these indirect attacks by automatically converting code to the any type. And all what we've done is formalized in Coq using the Iris framework. And if you're more questions, have a look at the paper, or ask now, or I'm welcome to chat about that later. So thank you very much for your attention, and yeah.
It's very interesting work. I would like to ask about, do you know about tainted types in Ruby? There was a lecture yesterday about it, which looks very similar to that any type. Do you know what is the difference between that any type and tainted types as a concept?
I think the big difference between this and Ruby is it's the setting of the sandboxing. So we are working like in a very low-level setting where like the untrusted code and the trusted code, we think of them as like C code. So they can write to the heap, they can forge pointers. Whereas in Ruby, it's a higher-level language, so you can attach tags and something like that to types. But we cannot do this in our setting because the untrusted code could forge such tags, and we need to prevent this in some way. So, but it would be interesting to see whether similar ideas can also be applied in this low-level setting to the tainted types.
Thank you.
Yeah.
What kind of properties do you prove about these wrappers? Like, are they retraction pairs or embedding projection pairs or anything? Or are they just two functions of that type?
Yes, that's I mentioned that briefly. So the important point is we actually only require that they're a function of this type, and this is actually, I think, key to the expressiveness of our wrapping system, as we've seen with these file example. As we will see, the thing is, these are not like if you export a value and then import it again, it's not guaranteed that the import will succeed again, because it might be that you're reusing it and then it will fail. So it's actually key that we don't put more restriction on these wrappers.